knowledge of both its derivatives and how they are useful for finding it. So let's consider some examples and well, train our eye for recognizing how to do any. First example. Compute the integral x to the fourth x plus y dx. So first we have just integration integrals, which means it's just finding the antiderivative. Okay, so it's integral of the polynomial, multiplying the function with the derivative is the sum. We know that if you find a function, well, three functions with derivative after something the x4, x, and 5, then there are some of the derivative equal to this sum. So it's the same as integral of x to the fourth dx plus integral of f dx plus integral of 5 dx. Then we use that information. Integral of x plus power n is x squared plus 1 over n plus 1. So it's x to the x plus 5 plus x squared over 2 plus. So here I have integral of 5. We can think about it if it's 5 times x to the power 0, or just guess that the function the derivative is equal to 5 times 5x. In the end of every answer with index integration, we add this last constant. So it stands here just to remind you that there isn't just one function whose derivative is the given one, there is a whole bunch. And they all differ by adding the part. So we have this expression 17, the derivative is not going to change, it's still going to be x to the fourth plus x plus 5. So this kind of integral is the simplest possible, just a sum of functions for which we know the integrals, maybe the sum constant, 1, 1, and 5. Any questions about this one? Okay, so let's solve this one. Integral of square root of t plus 2 over square root of t into t. So first difference, the variable here is called t instead of s, but that's no problem, we will just express the answer as a function of t. Second thing, here we have some square roots. They are not exactly one of the things we wrote. They are more or less the same thing as x to some power. So square root of x or square root of t can be re-expressed as t to the power 1/2. So you can rewrite this in a form which will be much more familiar. T to the power 1/2 plus 2, 1 over square root of t can also be written as t to some power, or power. Negative 1/2, so times t to negative 1/2. And now I will use the formula for the integral of s to the power n. So t to the power 1/2 over 3/2 plus 2 times t to the power 1/2 over 1/2 plus 2. This function is this derivative. And of course, if you want, you can always simplify a little bit. Like 2/3 t to the power 3/2 plus 4 t to the power 1/2 plus. rewrite each summon as a function in two reference. Questions about this? Okay, let's increase the difficulty even more. Now that we have integral of x plus 1 divided by 2 root of x. Now it's not really written as a sum of functions which you can recognize, a sum of functions which you can be easily transformed into functions which you do recognize. But we can transform this equation into a form which is a sum of functions which we can integrate. So how can we do it? Right now this function looks like a quotient of two functions, and we don't have a rule for integral of quotient. Yes, so okay, yes. Let's do it like this. So the idea was to write this as x plus 1 instead of divided by the root of x, multiplied by x to negative 1/3. Now we'll open the brackets. So integral of x to the power 2/3 plus x to the power negative 1/3. So if you multiply x and x to the power minus 1/3, it's the same as x to the power 1 and x to the power minus 1/3. Same as x to the power 1 minus 1/3, which is x to the power 2/3. 1 is x minus 1/3 is here. And now we can easily find this number. It's x to the power 2/3 plus 1/5/3, 5/3, plus x to 2/3, 2/3, and plus minus 1. So a third class of integrals which you know how to compute is this one, where some algebraic manipulation you can transform it into an expression which is sum of things which you can integrate. So remember this trick, that you can take a function which looks like, well, usually a polynomial divided by something like x divided by x to some power, rewrite it as just sum of powers of x by just dividing each of the monomials here by this power of x. So questions about this exercise? Let's compute that integral. So integral of 5 times 3 times 17. This one is pretty simple. It is more or less like the first example. It's a sum of functions which we can integrate quite easily. It's sum of 5 and 3 times cosine 19. Integral of 5 is, so what's the integral of 5? 5s. So 5s, but here the variable is t, so I will write it as 5t. And integral of cosine is sine plus 3 times sine 19 plus cos. So this integral was just a warm-up for the next one. Next one will be integral of cosine squared of t over t. So unfortunately, square of cosine is not one of the functions which we can guess easily what is the native derivative. So I can't remember off the top of my head a function whose derivative is square of cosine. So it's not really one of the functions from this table of integrals, but it can be transformed into an expression which is exactly of this kind of such an expression. Sum of things which are easy to integrate. So does anyone remember a formula which expresses square of cosine in terms of sum of things which are easy to integrate? So maybe constants, sines, cosines. Okay. 1 minus sine squared is a formula, but sine squared is as complicated as cosine squared multiplication. So does anyone remember a different formula which involves cosine squared? It's not really on the table. It's either you remember from this high school or not. So I'm talking about formula for double n of half and half. So I'm talking about formula which looks like this. Cosine of x is 2 times cosine squared of x minus 1. So this is double level formula. And what's good about it, it can express square of cosine in terms of just cosine. So in particular, cosine of t can be written as 2 times cosine squared of t over 2 minus 1, or cosine squared of t over 2 can be written as cosine of t plus 1 over 2. So you can rewrite this integral as integral of 1 plus of cosine of t plus 1 divided by 2. And this integral is now very simplified. It's 1/2 times the integral of cosine of t plus the integral of 1/2. So it gives 1/2 times sine plus 1/2 t. So this integral is an integral of similar kind to this one. It's not really a sum of simple functions which can be easily integrated, but it is in disguise. So if you remember some formulas from trigonometry, the double angle formula, then you can re-express this integrand, the expression which you're integrating into this integrand. So if you re-express this integrand as a sum of simple functions. Simple means simple to integrate. One of the things which we go over the last lecture. So we will discuss this kind of integrals, trigonometric integrals, a little bit later in more details, but basically we should review some formulas from trigonometry. Double angle formulas should be remembered. So remind those later, Thursday, but we will have to do a review for now. Alright, so questions about this integral? antiderivative is only a means to the end of finding actual areas under the graphs or actual definite integrals. So if you have a definite integral, so another example, let's find the integral of x plus 1 squared over x from 1 to 2 dx. So now I'm going to find the area under the graph of this function is 1 squared over x, or in other words, the integral from 1 to 2 of this function. So any suggestions? How can we find it? Yes, exactly. So what I'm going to do is just open the brackets and try to use one of these trees. So I'll expand it, x squared plus 4x plus 1 divided by x. And now I will use this trick of taking the polynomial divided by power of x and rewriting it as just sum of powers of x. Integral 1 to 2 x plus 2 plus 1 over x dx. For each one of those, I do know an antiderivative. Antiderivative of x is x squared over 2. Antiderivative of 2 is 2x. Antiderivative of 1 over x is derivative of 1 over x, power of 1 over x is 1 over x. And then I have to evaluate each one of these functions at the end points, at 1 and 2. So overall, I get 2 squared over 2 minus 1 squared over 2 plus 2 times 2 is 2 times 1. Plus 1 to 2 minus 1 to 1. And the answer is, so it's 4 minus 1 half plus 4 minus 2 plus 1 to 2 and minus 0. So it's 5 and 1 half minus and plus 1. So, first of all, please do appreciate the progress that we've made since the beginning of this lecture. We are now computing integrals, which means area under the graph of the function, for really complicated functions. Function like x plus 1 squared over x. And we even get answers which would look really complicated if we didn't know this fundamental theorem of calculus. Who would guess that integral the area under this function is something like 1 and 2 plus 5 and 1 half? Who would guess that there is a logarithm of this? But there is. And the second lesson is, well, do remember about these tricks. Try algebraic manipulation, try divide numerator with denominator quite explicitly, to bring a complicated expression to an expression which is easy to read. And it's really important to do many examples of integration precisely for the following reason. You have to recognize expressions which are easy to integrate. So you have to recognize that this expression is much easier to integrate than this one, so that the line will be kind of working you from here to here. Okay, so questions about this example? Yeah. So I could have also included the constant, but I didn't. And the reason I didn't is, suppose that here instead of x squared plus 2, I have x squared over 2 plus a constant. What will happen? I will relate x squared over 2 plus a constant at the two endpoints. For one of the endpoints, the plus constant will be with a plus sign. For the other one, it will come with a minus sign. And overall, it will get cancelled out. So for definite integration, when I relate the integral from somewhere to somewhere, I don't have to write constant. And it's kind of reasonable that the answer to a definite integral problem, which is kind of the area, it should be a number, should not depend on something. Other questions? So, even now, even after we dealt with this fundamental theorem of calculus, the set of functions which we can integrate is pretty limited. We can basically integrate only functions which are either are sums of the simple functions which we can integrate, or can be brought by some algebraic manipulation to such a form, some simple functions. It's a very small set of functions. But remember that when we differentiated, when we learned how to differentiate, we had several important results. Like what is the derivative of the product? What is the derivative of composite function? What is the derivative of motion? And every time we have a result about derivatives, we can translate it into a result about integrals. Kind of look at the result about derivatives, but kind of backwards. Not thinking about how to find the derivative of something, but trying to recognize when something is a derivative of something else. So let's talk about what's called substitution rule. Is the counterpart of the chain rule for differentiation. So recall the chain. If you know the antiderivative of f, or if you found the function with derivative is f, then you can differentiate the function f of g of x. So you can try to differentiate the composite function f of g of x. Chain rule tells you that it's the derivative of big F, which is small f, evaluated at g of x, and multiplied by derivative of g. So this is just the chain rule. Translated into some information about integration. What kind of information? If I want to integrate this function, if I want to find the antiderivative of f of g of x minus g prime of x dx, what is it going to be? Well, it's going to be basically f of g of x plus a constant. So now this rule sounds pretty complicated. If you want to integrate a function which happens to match this particular pattern, some function related and the value of some other function times the derivative of this other function, then you have just evaluate the antiderivative of the function f at the point g of x and very close. So for now, this rule tells you some information, but it's pretty complicated. So we will introduce some notation to make this rule easier to remember and easier to apply. So we introduce a notation u, a new variable u, which will be u of x. Then you can say that this integral of f of g of x, g prime of x dx, what is it? It's basically f of u plus constant, but this can be rewritten. What is this large f? This capital F is the antiderivative of small f. So now I get the following result. Integral of this function f of g of x, g prime of x dx is the same as integral f of ut, where u is g of x. In this form, it's much simpler to remember. And we will introduce even more notation. We will say that this thing is integral of f of u. So this looks like f of u. So it must be that this g prime of x dx is the same as du. So we'll introduce the notation of d of u is equal to g prime of x dx. And in this form, what we have to do is remember this simple formula. Integral of f of g of x, g prime of x dx. If you want to compute this thing, what you do is as follows. It is introduce a variable u, which is gx, g of x. You write down that the differential of u is in fact g prime of x dx. So this thing is basically a useful notation to remember this formula. And then this integral automatically translates into the integral of f of ut. So that's a substitution. In a box, that's the rule. So from the point of view of abstract reasoning, it's just the same as the chain. The chain rule of differentiation, if you write it in terms of integrals, becomes this rule. From the point of view of computing integrals, the important part is just how to apply it. So let's see some examples, some simple examples first. Let's integrate something like integral sine cosine x squared times 2x dx. So I'll start with an example which is really simple. I'm trying to find a function whose derivative is cosine of x squared times 2x. I will try to apply substitution. I'll make a substitution. I see here a function which is composite function. It's cosine, but not of x, but rather x part, 2x times dx, is just du. This integral is quite easy to evaluate. Integral of cosine is just sine of u plus a constant. So did we find a function whose derivative is cosine of x squared times 2x? Well, sort of. It is sine of u plus a constant, but you have to remember what u is. U is x squared. So we want to rewrite everything in terms of x. So we plug in the expression for u. And now we do see a function whose derivative is cosine of x squared times 2x. We can then check if you want to find the derivative of sine of x squared, the derivative of sine is cosine of x squared, and then the chain rule tells you to multiply this with the derivative of x squared, which is 2x. So in fact, this whole procedure of going from this function to this function to that function to this function is reversing the logic of chain rule. The chain rule would have told you that derivative of sine of something is cosine of something times the derivative of something. What you are doing here is reversing the logic. Here I see cosine of something times the derivative of something. I give a name, u, whatever is something, is cosine of something. I call this argument of cosine the name u. Its derivative happens to be the dx, and then the inverse of the chain rule tells you that the integral is just sine u. So that's how this substitution rule works. So, questions about this example. So this example is, well, it is quite easy in the sense that I try to write a function which is quite explicitly of the form a function of g of x times the derivative of g. So something that will fit this pattern quite perfect. But the substitution rule can be applied in slightly more general situations. We'll see in a second. So before we go to the more general situations, more complicated examples, once again, questions about this simple example. So then let's try a little bit more complicated example. So how would we argue? We would argue that this function resembles e to some power. That's the good thing. The bad thing is it's not quite e to the power x, which you know the derivative just from memory. It's e to the power 5x plus 7. So the idea is, let's take this 5x plus 7 and give it a name. And call it u. Substitution rule tells you So the integral is going to be transformed according to this formula. D of u is going to be derivative of 5x plus 7, which is 5, and dx. Now we recognize that this 5 times dx does appear here, so this will have integral e to the power u times du. And the answer is e to the power u equals constant. And once again, you want to translate everything back in information about functions of x. So the u is 5x plus 7. So just another simple example. Once again, questions about this simple example.
Does du always fit so nicely back into the equation?
It does. So that's just a special feature of these first two examples. Later we'll see examples where it doesn't fit that nicely. Maybe let's actually go to such an example. So let's try to integrate x squared times sine x2. It's going to be just very slightly more complicated than the previous examples, but almost as easy. So once again, I'm going to integrate this function. I see that it involves sine of an argument. I do remember that I know how to integrate sine of just x, sine of a variable. I don't really know how to integrate sine of some complicated expression. So I'll try to make this complicated expression into the numerator. U will be x cubed. Substitution rule tells me du is going to be derivative of x cubed, which is x squared times dx. Now I don't really see here 3x squared dx. But I almost do. All I see here is just x squared dx. So I'll take this equation and rewrite it as x squared dx is 1/3 of du. And now I can rewrite this whole integral as an integral sine of u times 1/3 and d. This 1/3 goes out of integration, so it's 1/3 times integral of sine is negative cosine. And last step, plug in u is equal to x cubed. So it's minus 1/3 cosine x cubed plus x. So in this example, we did not see du exactly inside of this integral, but we almost did. We've seen x squared dx. It wasn't exactly du, but almost. Okay, so I don't have another short example, so So maybe I'll also go to here.